Still some people coming in. Okay, well, I think we'll get started. So thanks everybody for coming. This is just the second meeting of the seminar series this semester, so it's nice to have everybody joining us again. I'm happy to introduce our speaker today, Dr. Ioan Nistor, coming from the University of Ottawa. He is a professor of hydraulic and coastal engineering there in the Department of Civil Engineering. He's actually also their assistant vice provost for graduate and postdoctoral studies. So I'm glad he still has time for things like this with more administrative tasks there. But he works a lot on coastal engineering, problems of hazards on infrastructure, coastal erosion, hydrodynamics. So it's nice to hear from him with our burgeoning ocean engineering program. He's very accomplished in academia. He's associate editor of several different journals, and he's won awards for his papers and as well as his teaching. Prior to joining the University of Ottawa, he spent several years as a design and consulting engineer in Montreal, actually, working on international Canadian water resource projects. So with that, I'm going to let him tell us about his work, and thanks so much for joining us.
Thank you so much, Chris, and thank you very much for the invitation. Hello, everyone. As mentioned, I'm a coastal engineer, so what I'm going to present today is are some lessons that I've learned during some field investigations and some research that we're conducting at the University of Ottawa in collaboration with a number of water institutions. So I'll just share my screen here. And I guess you can see can you see the presentation now?
Yes.
Perfect, very well. So just some lessons from post-disaster forensic engineer field survey and experimental modeling. So I'm a civil engineer, and I understand that the audience may be different than your typical civil engineering program. So it's not very technical, if you want, in details when it comes to civil engineering. So I guess you'll be able to follow me. And I look forward, if you have any questions, I'd be happy to reply. So the presentation is going to be focused on loading generated by extreme coastal flood events during tsunamis. But this is applicable to the case of dam breaching or dike breaching, or in the case of the flash floods. So essentially, it's a non-steady type of flow that carries, for example, debris and impacts infrastructure that it's located in its way. So just to give you an illustration of what debris means in the case of a tsunami event, this is a video filmed in the 2011 Tohoku tsunami in Sendai. And here you have an example of the coastal inundation generated by, let me see if I don't think that the sound on this one works, but it's essentially has been filmed in March 11, 2011, when the tsunami is actually flooding the Sendai plain. What you will see here is a turbulent bore. It's essentially the front of the wave that's broken, and it's pushed inland by the volume of water contained in the tsunami. And as you can see, there is significant entrainment of debris in this flow. You can actually see that lots of people are still trying to make their way out from the path of this incoming flow. Again, the subduction zone was very close to Japan, and then that's the reason why the time available for people to evacuate, even during a tsunami alert that functioned very well in Japan, was very limited, in the order of 20 to 25 minutes. And that's a very flat area. In the case of Sendai, it's a bit lower towards the south, comparing to the place of, say, the northern Tohoku, where you have very steep mountains right near the shoreline. So it took long for people to reach higher ground or to reach some of the tsunami shelters. So go to the next slide. Here you have some example of floods in Chile, in an event in 2015 in Chile. Gives you an idea of the size of the debris. And it's an interesting to notice also the reaction of the people that are watching this flood. You will see large trucks that are going by now, large containers, and you will see that people are still very relaxed and calm as this massive torrent of water goes in. And then as the water comes rushing by with even higher flow rate, people are only then trying to make their way to higher ground. But this gives you, there's a big truck they're carried by the flood. So it gives you a bit of an idea of what debris means and the potential effect when it comes to impact on structures, right? And whenever we think of swimming under such conditions, or people think that swimming is gonna, it may work, but it's very difficult in a built-in environment where the water entrains a lot of debris. So essentially, for the case of the debris motion, natural disasters such as on-land tsunami flow or extreme events, or aging infrastructures, such as in the case of the dams or dikes that breach, can lead to extreme flow conditions. And typical characteristics of these flows are high energy and high momentum, as well as significant debris entrainment and displacement whenever we are in a built-in environment, say in a city or in a port or in a coastal area. This is a typical example in Miyako Port, a very small actually city on the coast of Japan during the March 11, 2011 tsunami, where you see a lot of entrainment of containers and also cars located in this area. So in terms of research problem, we're interested in debris loads and effects. And we're having two aspects. One, debris impact, single debris impact in the form of a dynamic load. So debris carried by the flow and impact in the building, as well as debris damming. And I'm going to illustrate what that means. It means that the debris wrap around, for example, a structure or accumulate on a piece of infrastructure, and then they exert a static load as the flow pushes in. They expand the area and the drag of this building. There is some flow acceleration effects, as well as scour induced around the building that can lead to failure. Now, in terms of when we try to evaluate the influence of the debris, this is very difficult because, first of all, it's difficult to identify their location in the field and what happened to the buildings, because often buildings failed as a result of the debris impact. There is a strong random nature of the debris motion. So it's hard to predict precisely how the debris are going to move in such a turbulent event. And it's also hard to determine what was the debris source, unless we had pictures from before the event, and sometimes we did. And also due to the transient nature of the debris motion, they move sometimes erratically or randomly. We have sometimes faster flows, slower flows. And with the inertia associated with the debris and the presence of obstacles, it's difficult to assess their motion. Just a few words about tsunami for some of you that may not be familiar. I've done my PhD in Japan more than 25 years ago. And that's when I became interested in tsunami. I come originally from Romania, which is a country that has only about 250 kilometers. It's 150 miles of coastline. So we have no debris, barely any big storms. So, but I was very curious about tsunamis because I was living in Yokohama. The first training that I've done as a grad student was the training for tsunami and the training for earthquake, together with all the other international PhD students. And it comes from the Japanese word tsunami, which means harbor waves, because the Japanese have noticed the occurrence of these waves whenever they were coming silently, because they didn't have any warning systems at the time. But for the case of Japan particularly, the people were able to somehow identify the fact that whenever they had a large earthquake, possibly along the coastline, there would be a large tsunami. So people would be able to take refuge to the higher ground. One big exception, for example, was 1960, where the big tsunami in Chile, the largest tsunami ever recorded in recent decades, has generated a tsunami that traveled almost 24 hours across the ocean and flooded regions in Tohoku, and people were killed actually in Japan because of this tsunami. And from the time on, people have installed the tsunami warning systems in the Pacific Ocean. So what happened in the case of the Tohoku tsunami, and how do tsunamis occur? Essentially, we have two tectonic plates. For example, here, the Pacific plate, just east of Japan, is being subducted by the Eurasian plate to the right, where we have Japan. So what happens is that in the motion of subduction, at one point, there's a continuous deformation over hundreds of years or tens of years, suddenly there's a sudden release of this deformation with an uplift of the bottom of the ocean, in this case, the Eurasian plate, and some, in fact, subsidence in Japan, and the data has proven this. And then a wave forms at the surface of the ocean, and the waves propagates depending on the orientation of the fault line. In this case was east-west mostly. But it travels over very long distances in the ocean, and the wavelength of these waves tend to be significantly larger than those of the wind waves. So that's why they're called long waves. In the case of the wind waves, and many of you, since you work in marine science, you would know that they, in deep water conditions, perform according to the linear wave theory. You have the circular motion, and deeper, you have less effects from the presence of the waves. However, in the case of the tsunami waves, the wavelength, again, is very significant, to the orders of kilometers, of tens of kilometers, or even hundreds of kilometers. So therefore, their velocity, for example, is only dependent on the water depth, the celerity, the speed of the wave. And therefore, someone can calculate the arrival time of the tsunami, and that's what the initial models were based on, if we know where this has occurred in the ocean, and we know the bathymetry along the transect to that particular epicenter. In the vicinity of the shoreline, there's some amplification, and the reason for that is essentially, this is something we've done for kids at school with one of my colleagues, Professor Murthy, who's one of the first tsunamis. Essentially, the uplift of the bottom of the ocean generates a relatively small wave on the surface that travels at high velocity. Because again, velocity is a function of the water depth. They propagate almost as a shock wave throughout the ocean. Two things happen as they propagate towards the coastline. This volume of water that has been displaced by the uplift of the bottom of the ocean gets squeezed by the upsloping bottom. So it's physically, if you would sit on the top of this tower, you would see how waves form to become bigger as you watch the ocean. It's an interesting phenomenon. If you would have a very high tower, you would see how they literally appear from nowhere, from out of nowhere. And the wave height increases, the velocity of the wave, the speed of the wave decreases. The only thing that remains constant is the wave period, which is of the order of minutes or tens of minutes. As they propagate towards the shoreline, they break and they inundate the coastline. Now, the breaking wave that you see there is a physical impossibility. We just put it there to convince the children that the waves eventually break and advance inland. In terms of tsunami coastal inundation, there is a strong similarity between the wind waves and the tsunami waves. The wind waves also have this uprush motion in the swash zone of the coastline. It's just that the volume of water contained within a wave is relatively small. The wave length can be, say, 50 meters, 200, 300 meters. In the case of a tsunami, the wavelength is significantly longer, and therefore the front of the wave breaks and the volume of water in the rest of the wave advances inland. So in terms of research, how did we all start all this research? Essentially, when I went in 2004 in the Indian Ocean tsunami, we went to Banda Aceh, then to Indonesia, then to Thailand, then we went to Sri Lanka. And when I came back, I was with some structural engineers, and they asked me, can you give us the pressure induced by these extreme events on the structure? So I went back, and I remembered at one point that there was this old formula of Hiroi where we have a uniform dynamic pressure distribution, and there was a so-called conservative value. And I said, well, maybe we can use this. And I consulted with my colleagues in Japan. Some of them were still using the formula of Hiroi. It didn't make any physical sense to me to have a diagram, a uniform diagram over a certain water depth. So we needed to do a bit more research. So essentially, we went from this in 15 years, we went to this type of diagram, which is something that we developed numerically and experimentally. And you can see that there's a time history of the pressure. Here you have the time, and then you have the pressure and the height of the cloud. There's a time history of the evolution of the pressure on a structure. And that allowed us to come with more refined diagram, more realistic, to say, diagrams that a structural engineer would be able to use and determine the load on a building. How did we do this? Using physical and numerical experiments. So essentially, the way we organized it, we had, first of all, we had three components. One of them was the forensic engineering field surveys, and those have provided tremendous number of ideas to us, from debris, hydrodynamic loading, scour around buildings, and so forth. So with some of these ideas, we tested them in the lab, and that's for example, a case of debris impacting an instrumented structure with a dynamometer and its pressure transducers to look at the impact of the debris. We also developed some numerical models that we were using to reproduce some of our experimental work. That's a SPH model to look at the hydrodynamic loading on the building. And the final purpose of all this work was essentially to come up with design guidelines for engineers, such that engineers are able to design, for example, structures or only critical infrastructure, in fact, which is located in, say, tsunami-prone areas or flash flood areas. So what we did for that, mainly with respect to debris, I'm talking only debris at this moment, we did a lot of post-tsunami forensic engineering surveys. And these are some examples of debris that we pictured in a number of places that we visited and we surveyed following the event. So some example, in 2004, we went to Phuket and then to Banda Aceh, which was the city most damaged and closest also to the epicenter of this massive earthquake. And at the time in the Indian Ocean, there was no tsunami warning system because the events were considered extremely rare. Just to illustrate a bit the impact or the size of the tsunami, I'm gonna play a little video here, and you have some sound. So it gives you a bit of an idea of the, and this is about 4.5 kilometers, so about 3 miles, 2.7 miles inland from the shoreline in terms of the maximum run-up that was measured in this close to the city of Banda Aceh, that we measured was 48 meters. Just to give you an idea, that was run-up, not the inundation depth, but the inundation depth in many regions of Banda Aceh close to the shoreline was between 15 and 20 meters. It gives you a bit of an idea of the force of this type of events. So these are typical images of buildings that were affected. The one to the left is in Nantong, Thailand, is a resort, which was up north from Phuket Island. To the right here, you have the pictures from Banda Aceh in Indonesia, where you see debris impact in the area, around the area where you've seen the previous video. This is another example here of debris impact in Banda Aceh, where you have debris accumulation, debris loading. And then we had even larger debris, and I'll come back to this question of extreme debris impact and how do we design for this type of buildings. This was an area, again, where you can see, this is about 1 kilometer inland, where you see a lot of large shipping, large fishing boats for the region of Banda Aceh. And maybe this is one of the most interesting ones. This was a large electric power plant that was donated by the Japanese government to the city of Banda Aceh. This was anchored about 3 miles offshore and was carried inland about 2 miles in Banda Aceh and cleared the path of destruction through the city. It's essentially a very large ship. When I approached that boat, I thought we're close to the harbor, but we were in fact about 2 miles away from the shoreline. Some other example of the work we've done is the post-tsunami field survey in March 11, 2011 Tohoku tsunami. These are some examples of some of the data that we used for before we went and did the survey to look at the regions that would be of interest to us. This was data that was collected by the Japan Society of Civil Engineers, and you can see run-ups at the time, run-ups of up to 30 meters. In fact, there were higher run-ups than 30 meters with the later data collected. You can see a bit of a lack of data here on Fukushima, where the nuclear plant was located. So by using this type of information, we decided which cities, for instance, would investigate. And this was, by the way, under the AAC banner that this trip was organized. And just a quick illustration again of the hazards involving debris motion, several images. of the tsunami overtopping some of the tsunami walls, and you'll see a large number of debris in several locations. This is Tsuchi. And this wall here was designed based on some historical events from 1896 and 1933, two major large tsunami events that were considered the largest possible in the area. In reality, they were overtopped by this 2011 tsunami. And you can see, again, for a port, large number of ships, large number of cars, large number of containers, for example. So following this, again, some people here were able to actually take refuge to higher ground, like the people that actually filmed this clip. Another 23,000 people perished during this event, although, again, the alarm was given on time. You can see from the same area, the waves propagating inland, and you can slightly see on the other side the edge of the tsunami wall that eventually was overtopped. These are images from Sendai Airport, which is a few kilometers inland from the shoreline. In fact, I had visited and took a flight from this airport in February 2011. And you can see as the tsunami coming in, it entrains a large number of cars and vans, large pieces of floating debris such as containers. And it provides an illustration of the type of loading that is actually generated on infrastructure, not in the form of hydrodynamic loading, but we can see now debris accumulation and debris damming. And we're trying then to quantify this type of debris. So during the field investigations, what we've done a number of measurements with respect to many things, like the spatial extent of the flooding, the water elevations, the hydrodynamic loading. But with respect to debris impact, essentially, we surveyed a number of interesting places where we were able to identify the size of the debris, such as this truck, which was 12 tons, for example. We could measure also some of the elements that were impacted, such as the poles, the electricity poles here. We took samples of concrete and steel, and we were able to actually trace back and calculate, for example, the velocity of the flood in this area. We essentially knew the water levels or the maximum water level in the area based on tracers on buildings, but we didn't have the velocity. Now, by doing this type of reverse calculation, we were able to get the flow velocity and then apply that flow velocity to other buildings in the area that were close to collapse. And typical example of when we talk about debris damming, especially after the 2004 Indian Ocean tsunami, people have suggested using, for example, collapsible walls in the case of buildings, because they say, you know what, if the walls are collapsible, the water is going to go through the columns of the building and you won't have any massive load, hydrodynamic load transmitted to the structure. Now, what happens, and we've seen this over and over in other surveys, in a built-in environment, that's valid only for the first row of houses. As soon as you move to the subsequent rows of houses, there's a lot of debris that accumulates around the buildings. And what happens is that the area exposed to the hydrodynamic flood increases, the drag exerted increases as well. So in reality, you have more accumulation of, an increase in the hydrodynamic forces comparing to the absence of the collapsible walls. The other question that came was, how do we design for this type of impact? Do we design for this type of impact? And clearly, the standard that I'm going to talk briefly makes today or now some provisions for so-called allows for progressive collapse prevention. So what it means is that for certain buildings which are deemed as critical infrastructure, such as a tsunami shelter or a hospital or a police station, we can design in such a way that we design the building overall to the loading exerted by the hydrodynamic forces debris, but we also design for the case when a number of structural elements, such as say the columns on the first row of columns of the building are being damaged. We design the building in such a way that the building still withstands and remains functional, even though, say, the first row of columns has been destroyed. So we can allow for this type of design. And these are all lessons from field. A final survey that I'm going to talk a bit is just the one in Palu, Indonesia, which was a smaller event, a localized event. in Indonesia as well. And here we looked also at the impact of debris and debris damming on structures, among other things. So when it comes to standards, there were a few standards, and I'm not going to insist too much on the FEMA P646 from 2012. It made provisions for debris impact load, and it calculated the maximum load. So it's a deterministic type of model using the mass coefficient, using the flow velocity, using the debris stiffness, and the mass of the debris. So by applying this formula, one can get an impact, punctual impact point that can be applied to a structure depending on what the judgment of the structural engineer is. The velocity of the water, because it's difficult to measure during an event, unless we have video recordings, which only happen really in Indonesia and also in Japan, is estimated either using numerical modeling of the coastal flooding or using some sort of an analytical formulas developed by coastal engineers based on the run-up and elevation of the structure. They also made some provisions for damming, which included the modification of the drag force to be able to account also for the increase in the force. So the drag force depends on the density of the fluid, on the drag coefficient, the width of the structure, the water depth, and the velocity of the structure. So when it comes to standards, why did we do this work? There was no standard to design structures against tsunamis, written in mandatory language, such as the wind code or the earthquake code, for example, seismic code for structures. So in 2011, there was a ASC Tsunami Loads and Effects Subcommittee that was established in Hawaii in February 2011. And in 2017, there was the first edition of the Tsunami Loads and Effects, Chapter 6 in ASC 7 standard. The second revision was recently finalized of the code, and this is now available from ASC. And in this case, the debris model is based on a 1D bar, where it assumes that the impact force depends now on the importance factors of the structure. We won't design all the buildings against tsunami loading, just the critical infrastructure. Depends on the orientation, because we notice that whenever tsunamis can hit straight on, but most of the times they hit at a glance. So you have to account for that. Depends on the flow velocity, depends also on the rigidity of debris, and depends on the mass of the debris. So, for example, there's one thing when you have a big boulder of concrete that hits a building through tumbling, and there's a different thing when you have a car that wraps around, for example, a column that has a different rigidity. And impulse duration is also important when we determine, for example, the loading on a building. So in terms of not only the force is important, but also the spreading of the debris. So the new standard made some provisions with respect to how do the debris spread. And why is that important? Because you want to know, if you design a building near an area where we call it here the debris site, you want to know what are the chances of that building to be hit by a piece of debris. And if that building is deemed as critical infrastructure, we want to make sure that we design for it. So the assumption of the model, based on empirical data and observations from the field, is that if we have a debris site, the debris are going to spread on an angle of 45 degrees as the water moves in. And then when they reach, for example, 3 feet inundation depth, they're going to come back in the form possibly of another 45-degree cone. Now, so everything that's within these cones, deemed critical infrastructure, had to be designed for debris impact. Now, there are some limitations that it's based on limited post-disaster survey cases, and also it's site-specific, depends on the topography of the ground, and there was no experimental and numerical validation. So one of the research that we conducted in the second round of revisions of the debris was to develop a probabilistic framework for assessing debris hazard in these extreme flood events. So essentially, instead of using a deterministic model where we say all the buildings in this area are going to be hit by the maximum debris with the maximum force straight head on, we this time decided to do an assessment where we can determine the probability of impact. What is the probability of this design site to be? Is it 100% or is it maybe 60%? What's the magnitude of the loading as a function of the time history of the velocity of the training flow? So this would lead to clearly to an economic design of the structures located or deemed as critical infrastructure. And that's what the seismic engineers do. So what we did, for instance, this was during one of my sabbaticals in Waseda University in Tokyo, where they have a small wave basin. Essentially, we tried to do some experimental tests to look at the debris spreading. Very simple test. And we used the so-called smart debris system, where we modeled scaled down 1 in 40 debris containers. And we fitted them with some sensors that we can trace with the aid of Bluetooth antennas located here at the top on the frame. We had some sensors so we can trace the motion of the debris. And also we had an accelerometer to determine the acceleration of the debris on the 3 axes, so we can determine the forces exerted on them. So essentially what we had was generate a wave in front of so-called an apron of a port, a solitary wave. The solitary wave would break at the edge here and then will push the debris inside. So we also developed an optical non-intrusive debris tracking system to confirm our spatial data with the Bluetooth sensors. And this enabled us to determine the spread angle of the debris. So a typical example here, what you'll see is the wave, the solitary wave coming from the left, breaking at the edge of the apron. And then with the video analysis and this tracking algorithm, we're able to determine how these independent debris were moving across the apron. So the reason why we did this is that we wanted to validate some of the provisions of the standard, its first version. So this is the type of result that we would get with a certain amount of error in terms of debris tracking. So the question that we had was, is this 45 degrees cone accurate or not? This is a typical example of the test that we were doing here. So what we came up with was this type of graphic, where what you see here is the number of debris on the abscissa and the spreading angle on the ordinate. So you can see that with an increased number of debris, all the way to 18, for example, in this case, you have more spreading angle because you have also a lot more interactions, debris-debris interactions, and more complex interactions with the flow. We also looked at the spreading of debris in the presence of obstacles. And to the left and right, you have in black the 45 degrees angle, and with different colors is the motion of the debris as they moved across the apron. So we concluded that the prescription of 45 degrees of the standard was somehow accurate for very standardized conditions. Of course, situation is different where you have a valley or you have a mountain right on the side of the. Some other things that we've done is at the University of Ottawa, we have a flume where we can generate dam breaks, because there were several researchers that demonstrated in the beginning of the 2000 that the dam break wave is actually very similar to the one generated by a broken tsunami wave advancing inland. So a lot of researchers use the dam break wave instead of the soliton waves. First of all, it provides a longer duration of flow, which is closer to the actual coastal flooding. And from a hydrodynamic point of view, its characteristics are conducive for use to simulate tsunami flows. And especially when you have debris which are being entrained, the solitary wave sorry, may not have enough volume to actually displace some of these. So what we had here essentially was we have a new flume now. This is the old flume with the small, we have a much bigger flume with a big tsunami gate. But essentially, we had a column that was installed on a dynamometer that can measure the impact force, pressure transducers, ultrasonic wave gauges to measure the water level around the column. This is the installment this is the load cell at the base of the column. And in the end, what we tried to come up with was a probabilistic formula with respect to probability of impact and force when it came to a debris being moved from one location inland by the port. So essentially, we came with some curves that provide the probability of impact of this at this location from a debris source. They give a probabilistic assessment of the velocity of the debris as they move inland, and also the probability of the force reaching a certain value depending on the initial location of the debris and the spatial extent of this location. In terms of the debris, impact load, we're trying to solve some other issues. We try to consider the debris velocity orientation, which are not considered properly in the current standard. And we also need to examine the influence of multiple debris. So that's the reason why we do this type of testing, where we're trying to simulate impact of multiple debris. The current standard makes provision for one debris impact, and we're trying to develop this probabilistic approach when it comes to possibility of impact and the force exerted on the building, depending on the type of debris. The way we do this is using the same type of dam break method, and we're capable to isolate the impact of multiple debris on a column. Sometimes you have the bounce back and a second strike that occurs as a result of this debris, and this again is not being considered in the current standard. We do some investigation now on the debris damming loads, and there are two aspects. For the case of the steady state flow conditions, this has been investigated in the past, particularly by river engineers. And this is a typical example where you have a mix, and we've done these tests also in our lab, where we have some piers, let's say, of a bridge, and to the left you have debris accumulating, a mixture of small debris, large debris, containers, and poles. And two things you'll notice: an increase in the water level, so the backwater effect that occurs upstream of the bridge, with an increase of the scour of the velocity at the base of these piers, with added scour that occurs. That's for the case, again, of the steady flow conditions. However, for the case of the unsteady flow conditions, the effects, and this is typical for tsunami or flash floods, the effect is much more significant depending on the flow conditions. You have rapid accumulation of debris, the formation of the debris dam, with significant differences between the upstream head and the downstream head. And that's consistent with the observations that we've seen in the field when it came to scour generated around these buildings. Huge amounts of scour. For example, in Japan, we've seen places where we had scour of 20 feet for the presence of the tsunami, at what we assume inflow, for example. So we need to consider the forces as a result of the debris damming, the backwater effect, and the flow accelerations, and these are not yet included in the tsunami standard. We do some numerical modeling as well, and this is a typical example of an SPH model of the simulation, experimental simulation that we conducted in Japan. What you see here is a stacking of the debris in the form of the containers. And you'll see the formation of the solitary wave from the right, and then they're being pushed over the surface of the apron by the wave that forms. And again, this one here, oops. Normally we would have to see them being pushed in, and yeah, it doesn't allow me to get past that. Okay, so other things that we do with this numerical model, essentially we're trying to look at the type of impact. We have different impacts depending on the hydrodynamic characteristics and debris location and the structure location. And we want to account, for example, for the impact of debris, the orientation, the subsequent force exerted as a function of the impact and the flow conditions. One of the last tools that we're working on to develop are agent-based models, which are used to assist the urban planners and disaster management planners who are working in tsunami-prone areas. And this is a typical example of a coupled model. So it's essentially a tsunami inundation, generation, propagation, inundation model, which is coupled with an agent-based model. We use this one for the island of Vancouver, the western seaboard of the island of Vancouver, that's just north of Washington State, facing the ocean and facing the Cascadia Fault, which is the major mega tsunami generator in the past in terms of hundreds of years. The last big one was in 1700. So the city here has asked us to assist them with the optimization of the location of a tsunami shelter and with their current evacuation plans for the case of a large tsunami. It takes about 15 to 20 minutes for the tsunami produced by the Cascadia Fault to reach this area. So what you see here in small dots are either tourists or locals in the summer scenario. During the day, we have different scenarios: day, winter, summer, winter, and day, night. And you have a number of tourists and locals on the beach. Some of them are located here in the city. So what we're trying to see, what you will see is essentially the tsunami coming from the southwest part. And you'll see that these small dots, or the agent based, which are the people are trying to escape using the routes that we program. And all these agents have properties. Some of them are old people, they move slower. Some of them are kids, they move slower. Some of them are tourists who do not know where the route of evacuation is properly. Some of them are locals who actually train every year. And I can tell you that what we're trying to do now for the tsunami evacuation, we are equipping the local people with 100 GPS trackers. And during the tsunami evacuation system, then we try to calibrate the results of this model with the actual facts. So let me play. Here you'll see the people all they're trying to run now. They're going to the tsunami evacuation as the alarm was given. You can see the time from the occurrence of the earthquake. And now you will see people have started running and evacuating, but you'll see that the big wave, there's a withdrawal, and then there's a big wave coming in very fast. And what you're seeing in dark spots here are all considered casualties. So you can actually see along some of these routes, a lot of the people have already theoretically lost their lives. Now, this type of tool will help the local community to actually plan for better evacuation routes. Or, for example, let's say this is called the Chesterman Beach. Maybe in this area, we recommended the location of a tsunami shelter in the form of an elevated platform, so that people do not have to trek through the forest to the higher ground in this particular area. So some of the engineering lessons, first of all, when it comes to field investigations, one thing we learned is that the current design standards do not properly consider the loads associated with tsunami events. Debris induced loads and effects which are critical to design when it comes to structures. In the case of experimental research, it's difficult to assess the transport and load, mainly because of the random nature of the debris. So you have to do a lot of repetition, and that's why we decided to go to a probabilistic approach to assess the chance of impact and the size, the magnitude of the force, depending on the distance and location in space from the original location of the debris. We're trying to move towards this probabilistic approach. In terms of design standard, significant improvements have been made in the second round of the standard based on research that has been conducted. And some of it that I've shown here. And in terms of future research, debris damming and multiple debris impact remains a significant item of research, and we're trying to focus on this. And there's very little on unsteady state flow conditions when it comes to debris. And additional influences such as added scour due to the presence of debris dams, for example, or flow accelerations, are not well understood, nor are they incorporated in the standard. So finally, we're trying to develop some numerical models to validate, to be improved and validate, to be applied for the design phase. So I think these are some small lessons when it comes to debris. Now, we have similar research on the scour, and scour associated with or without the presence of debris. We've started with hydrodynamic loading, and I've shown you in the beginning a diagram, for example, of the hydrodynamic pressure. Some of these things have been significantly improved. And again, the research that our group conducted and the research of a lot of the tsunami researchers around the world are based on lessons and observations from field investigations. So I'm a strong supporter of conducting this type of forensic engineering surveys. This concludes my presentation. And if you have any questions, I'd be happy to reply.
All right, thank you so much, Dr. Nistor. So I can help field questions. You can raise your hand or just go ahead and unmute or type in the chat. Any way you'd like to ask a question. So questions from the audience?
I have a question.
Sure.
You might have answered this. I had to step out for a moment, but are these same methodologies and processes being applied to anything with debris loading on storm surges, like from hurricanes? You know, we would be highly interested in such a
Yep.
program or technology down here.
So I can tell you that what you've seen here is and it's interesting that you asked this question because we always had this debate. Clearly, the methodology may be very similar. It's just that for the case of the storm surges, particularly for the case of the eastern border, particularly of the United States and even Canada, the flows tend to be less rapid than in the case of the tsunami, for example. But you would apply exactly the same technology. You have debris damming that forms in the case of storm surges. There's an interesting video because we always have this debate with people who work on storm surges and versus tsunamis. But there's a very interesting video of a storm surge that's been modified by the presence of the reefs in the Gulf of Leyte, the Haiyan hurricane in Philippines. And you can actually see, done by a camera, a storm surge that comes just like a hydraulic tsunami bore or a dam break bore. So you can have, depending on the bathymetry and the characteristics of the bathymetric characteristics of the island or the coastline impacted, you can have storm surges moving much faster than what you see, say, typically in the east coast of North America. But the methodology would be essentially the same. It's just that your flows are going to be maybe a bit less turbulent, and one may have also superposed waves that come on top of the storm surge, and those may generate additional effects when it comes to debris. Right? You don't have only the increase in the water level and the advancement inland, but you have the waves that tend to be coming on top of that increase in the water level. So methodology would be probably very similar, but you'd have to have also an experimental facility that would be able to do that. I know people in some universities also in the US, Oregon State and University of Delaware, Virginia Tech, there are people who work on debris under extreme flow conditions, and their focus is also on storm surge. So debris moved by storm surge. One name that comes in mind is Jennifer Irish, US.
I see. Thank you so much. Appreciate that.
Yeah.
Okay, any other questions?
Hey, Chris, I have a question.
Sure.
Hello, Ioan. This is Kamal. How are you?
Hi, Kamal. How are you doing? I saw your
Good, thank
message.
you. Yeah, very nice, very interesting seminar. Thank you. So I have a question regarding, so you can see even in the videos, it's almost like a mud flow coming in, right?
Mhm.
So other than these large debris, there's this huge sediment transport component, obviously. So, I mean, you showed the model SPM, and I was exposed to another model. I think it was GeoClaw, maybe.
GeoClaw.
Yes,
Mhm.
GeoClaw. So can these models, both hydrodynamics and morphodynamics, like do they incorporate all? Can they incorporate all those dynamics? And an additional question is, when you think of the large debris, let's say cars in this case, like in your experimental models, those blocks, I was looking at them and I was thinking those kind of like simulate or represent the cars hitting bridge piers and stuff like that, right?
Mhm.
So how about the amount of those? So that's dynamic, right? So whenever the tsunami comes, how much large debris will exist in the area will not be constant. So how do you account for that in your probabilistic analysis?
Good. That's both are very good questions, and they're lessons from the field. Reply to the first question. The first formulas or initial formulas used to estimate, for example, the hydrodynamic loading did not account for the presence of say, sediment that was entrained. And not only sediment, but lots of small particles of debris, which are being entrained in the flow. Now, this new standard actually accounts for that. And the density of the water is no longer 1.0, but I think it's 1.2 or 1.25. Don't quote me, I have to look to the standard. But it's, I think, around 1.2. And the reason for that, and there is a description there in the standard that says that due to the increase in sediment load and increase in debris entrained in the flow, conservatively, the density of the flow is 1.2. So if you would have a numerical model, it would be relatively simple. You would have maybe for a certain part of your computational domain, you would have a subroutine that would change the density of the flow, say 100 meters or 50 meters from the shoreline. The rest of your cells in the computational flow would have to use the density of the water as 1.2 instead of 1.0, the relative density of the water. So that's how the standard accounts for the presence of this sediment. Of course, that's a very good point, because to my knowledge, I haven't seen research on that. I think it was more of an engineering judgment. And any standard is, as you know, it's not a holy book. It's something that it's a living mechanism. When I look at for example, the erosion provisions in the first edition of the standard, they were very weak. Some didn't make too much physical sense. And I was part of the committee at the time, but we didn't have any other data. With the new research data, there is a much more nuanced now provision when it comes to calculating the scour. Now, going back to your second question, when you have large debris, how do you know? So when you do the design, there are some steps that the standard indicates. For example, if you're on, let's say you're in Oregon State, and you decide, first you have to decide where do you put your structure. And that's going to be a critical infrastructure. It can be, for example, the city hall, let's say, or the city library can be deemed as a refuge. So you know the location, you know where you know also the characteristics of this earthquake. So first, one would design the building to withstand the impact of the earthquake. Then the building, which is designed for earthquake, say in Cannon City, I'm giving an example, I know there's a structure there. Then what you would do a verification of the structural stability using the hydrodynamic loading and debris load. And for the case of the debris, as an engineer, you use your engineering judgment. You look at the map, you look at where this structure is being located, and which are the possible sources of the debris. Is there a port, which is located right perpendicular on the transect from the building to the ocean? Or is there a chance for the debris to move and impact this structure? So there's a procedure that provides, you have to draw a transect from the direction of the flow. You put your 45 degrees angle from the location of the debris, which you know, it can be a port where you have small fishing vessels or yachts, or it can be a very large harbor where you have big container ships. And then you verify if these things can impact your structure or not. If you have very large structures, very large debris that can impact your building, and they're, say, I don't know, 200 tons, 200,000 tons ship, obviously you need to move your library or your city hall, small city hall building in your tsunami shelter, because there's a big chance, there's a significant chance for that to be impacted by a large debris. So when you can design for certain types of debris, but you also have to be aware of the fact that you may need to avoid, depending on the size of the structure and depending on the size of the debris, you need to avoid that impact and relocate the buildings to a different place. This is usually done through a site-specific, and the standard makes provision for that. They say you need to do a site-specific assessment of the source of debris, location of the debris, the distance from the location of the debris to your point where you want to build the building and so forth.
Thank you.
All right, do we have anything else?
And I do apologize, I have some background noise here. We've got some construction next to us, so there's maybe some sound of trucks around.
I have one quick question. Thank you for that presentation. It was very interesting. I'm just wondering, kind of following up on Kamal's question, do you ever put sediment, different types of sediment in your experiments?
We do some tests. No, we had two PhD students who did two theses on scour around structures as a result of hydraulic bores, which are assimilated to tsunami inundation. The tests we've done, essentially what we looked at, the first test was development of the spatial development of the scour and the progression over time of the scour. The second test that we did with the second student were essentially not only that, but also measuring the pore water pressure variations around the structure to try to correlate the scour erosion rates, which are usually given in the hydraulic formulas just as a function of the shear stress, to correlate that with the soil characteristics, with the pore pressure variation. And we found some interesting results with them. Now, based on that type of study, you can actually make a recommendation of the type of feeling around the foundation of a structure that would be able to withstand a certain degree of scour. Or if you cannot ensure that, you can make provisions. In fact, the standard, that's what it does. It says, as a function of the water depth and the velocity, you're going to have that much scour around the structure with this size, because it's a function of the geometry of the structure. So what an engineer would do, would take that graph and would say, well, my foundation from a bearing capacity point of view has to be 10 feet deep. Because of the scour, I'm losing 6 feet. So therefore, I have to extend my foundation to 16 feet if that building will be deemed a critical infrastructure, as a tsunami shelter or a hospital that's a critical infrastructure. So that's the type of logic when it comes to designing for, but the tests we've done are still we did tests with gravel, which were scalable, and tests with sand, which they're not exactly scalable.
Yeah.
So that's where the
is that and specifically I should have been more specific in the flume experiments, because I noticed a lot of it. So you use sand sometimes in the flume experiments. Interesting. And does that it's sand and gravel, and then you have the scaling issue potentially. So did you notice differences? I couldn't tell in some of the videos that you showed. It looked to be clear water. Are there noticeable differences when you change the density of the fluid?
So the tests we showed you were only for debris. So those tests didn't have the sediment.
Okay.
The test, I have another presentation of that. The test is with clear water. Now, in the new flume, we have a new flume at the University of Ottawa, and we got $6.2 million in fact grant last year, where we built already the tsunami gate, which is now electromechanical. It's a 1.5 by 1.5 meter depth flume. We have a sediment recirculation system. So our plan is to have, and we have a wave generator, which is going to be built in this room. So we plan to do tests which are not with clear water, because the tests we've conducted are clear water. So that's another, you're very right, that's another limitation when it comes to scour. Whether we'll be able to reproduce the typical flow conditions from a tsunami, I doubt, because you have a lot more than sand. And it's not even sand. One thing that I've noticed in all these field investigations, when you go in the field, you have this very fine mud in many of these places, like a darkish mud, because sometimes it's deep water sediments that are being brought by the tsunami inland. It's not only the sand, it's this deep dark mud. Even the smell, there's a specific smell in these places that it's the same. It's this deep water sediment that we noticed deposited after the tsunami retreated. But in terms of provisions, when it comes to design for a scour, I think standard is better than what it used to be. I think the tests can be a lot more sophisticated than what we've done so far. But that's why you get ideas, and even your question, you get ideas from lessons with what you see in the field in some of these tests.
Thank you.
Okay, maybe one last question. There's a question in the chat. basically, is there anything special about the 45-degree spread that you chose, or is there data behind that?
Yeah, it's interesting that angle was proposed by Clay Nato, who's a professor at Lehigh University. He has done a field survey in Talcahuano in 2010 in Chile. And that initial provision was based on containers moving on the apron of the port in Talcahuano. So that provision, and it gives you an indication of how rudimentary maybe the first versions of the standards are. That was based on that empirical set of tests from the field, and the head of this tsunami committee, who was a consulting engineer from Hawaii. It's a very pragmatic person. Says we need to provide some sort of a guideline, but based on some sort of a data existing in the field, and that was the data. And to me, it was interesting as an academic. Sometimes you don't, but I've been a consulting engineer, so I know where it comes from. But they have to have some sort of a prescription. So we said, shouldn't we test this hypothesis? In what we've seen, and again, with a disclaimer, this is for very standard condition of flat port. Yes, 45 degrees is pretty conservative in terms of the spreading degree of containers or ships. Now, if you have boulders or you have big seawalls that are being broken, and they tumble as submerged debris, that's another question. So one of the former PhD students that worked with me on debris was a professor now in Quebec City at Ioan Nistor. He's going to do in the coming summer in their large-scale flume tests on submerged debris and how do they move and how do they impact and what are the changes. So this hasn't been done, for instance. And I guess the idea, I think people in oceanography have done tests on moving boulders ripped from for example, from reefs, submerged reefs, and how they are being displaced and imposed on the shore by storms, for example. So that's another type of idea that came from what we've noticed in the field.
Okay, great. In the interest of time, I think we should close. Everybody's free to go. And we all thank Dr. Nistor for giving us this great seminar. And if anybody still has a question, we'll leave the Zoom open for a little longer as people are signing off. So thanks so much.
Thank you very much, Chris. Thank you very much, colleagues. And we definitely appreciate it. I'd be willing to reply to any of your questions. If you need or if you want, you can send me an email to my email address. It's ionistor@uottawa.ca.
All right.
And I wish you a very pleasant weekend.